A 32-bit integer can represent values from around -2 billion to 2 billion. That's a wide range, but integers are exact. No fractions, no decimals. So, what happens if we want to represent something like 3.14 or 0.001 or even something huge like 1.23 times 10 to the 30s? In the world of programming, that's where floating point numbers come in. But how do we actually store them in binary? Let's find out. Welcome back to Drilling Sessions. In the last video, we explored how negative integers are represented in memory using bit-level tricks like 2's complement. Today, we are diving into how non-integer values, decimals, fractions, real-world measurements are represented using floating point types like float and double. We'll begin with a concept you already know: scientific notation. You can write 3.14 as 3.14 times 10 to the power of 0, but you can also write it as 314 times 10 to the power of -2. It's the same number, just expressed differently. We're breaking it into three parts: the sign, the significand, that's the actual digits, and the exponent, which tells us how to scale it. This format is called scientific notation in base 10. It allows us to express very large or very small values in a compact way. Now, here's something interesting. Any non-zero number can be written as a number between 1 and 10 multiplied by 10 raised to some power. For example, 42,500 becomes 4.25 times 10 to the 4th. 0.0075 becomes 7.5 times 10 to the -3. Even 1 becomes 1.0 times 10 to the 0. This specific format is known as normalized scientific notation. It means we always write the number so that there is exactly one non-zero digit to the left of the decimal point. Computers work in base 2, so instead of powers of 10, we use powers of 2, and the rule is nearly the same. Any non-zero number can be written as a number between 1 and 2 multiplied by 2 raised to some power. This is scientific notation in base 2. And just like in base 10, this form can be normalized. We express every number as 1 point something times 2 raised to some power. But how do we actually get to that form? Let's take a real example: 7.345. We start by breaking it into two parts. 7 is the integer part, and 0.345 is the fractional part. The integer part is easy. We convert 7 to binary. That gives us 111. Now comes the fun part: converting the fraction. To do this, we multiply the fractional part by 2 over and over again. Each time, we extract the digit before the decimal point. And we keep doing that. This gives us a sequence of binary digits after the decimal point. Of course, we don't go on forever. Floating point formats have a limit. A float can store 23 bits of fraction. A double gets 52 bits. So we stop when we hit the limit, or if the fractional part becomes exactly 0, whichever comes first. And if we do hit the limit, we round to the nearest value representable within those bits. Now we combine both parts. We take 111 from the integer side and tack on the fractional bits we just computed. The next step is normalization. We shift the binary point until we have exactly one digit to the left of it, and that digit is always 1. And now here comes a smart optimization. That leading 1, it's always there, so we don't store it, we drop it and only store what comes after the decimal. This is called the implicit leading bit, or the hidden one. It's not stored, but it's always assumed to be present. Now, what about the exponent? We said the exponent here is 2. Here's an issue. When we compare floating point numbers by their row bit patterns, which hardware often does, we want the layout to reflect the actual order of magnitudes. But if we stored the exponent as a signed integer, negative values would start with the leading 1 in 2's complement, which would throw off comparisons. And because the exponent sits in the middle of the floating point layout, not at the front, it's tricky to perform sign extension or magnitude-based sorting directly. So instead, we shift the range upward by a constant, a bias, which turns negative exponents into small unsigned numbers and keeps all exponent values strictly increasing with magnitude. This makes comparisons easier, keeps the layout clean, and simplifies the hardware design overall. In 32-bit floats, the bias is 127, so exponent 0 becomes 127, exponent 2 becomes 129, and so on. This lets us use unsigned binary values for the exponent field and keeps things simple for hardware. For doubles, the bias is 1023. Same idea, just more bits. So now we have all three parts: the signed bit, the biased exponent, and the fractional bits after the hidden one. And here's how they are laid out in memory for float and for double. And this is the formula the computer uses to reconstruct the number. And that's how a float is stored. But before we wrap up, let's talk about precision. Floating point numbers can store only so many digits, and some decimal fractions, like 0.1, don't have a clean binary equivalent. So when you try to store 0.1 as a float, what you actually get is a rounded approximation. Now imagine doing math with approximations. You can quickly see the problem. Let's say you compare the sum of 0.1 and 0.2 with 0.3. You'd expect this to be true, but it's not, because 0.1 and 0.2 are already approximated, and when you add them together, the tiny rounding errors cause the result to be just slightly off from 0.3. So, floating point numbers come with the caveats. They give us an incredible range and very efficient storage, but they do so by sacrificing exactness. And this is why comparing floats for equality is dangerous. Instead, we compare whether two values are close enough, typically using a small threshold called epsilon. Floating point math is fast, flexible, and powerful, but it's not perfect. And understanding its limitations is just as important as understanding its structure. So today, we explored how floating point numbers work under the hood, from scientific notation and normalization to binary layout, precision trade-offs, and common pitfalls in floating point math. Thanks for watching, and as always, happy coding!